So the interesting question is what we're going to address next, which is, which one is bigger? It would seem like if they're equal, you'd have this problem right when you hit that force. Isn't that weird? And yes, you're right, it gets weird. Okay, so let's get it weird here. So this is something that sort of confused people for 2,000 years, right? So if force causes acceleration, what's going on here, right? Why can I push and get a constant? I'm pushing with my hand, I'm getting a constant velocity, I'm not accelerating. Well, it's because of friction, right? So let's go through just the numbers real quick. Or we could skip that and do more interesting things. Let's do that real quick. Okay, so let's apply a force. Apply a force and get constant velocity. And question mark, exclamation point means we're confused, and I'll put Aristotle to make it clear that you're probably not confused about this. We're just going back in time before we knew about friction and say, how is it possible that I'm pushing it and it's going at a constant velocity? So we'll just go through the numbers real quick. Right? We'll do this one really fast. Here's my hand pushing it. Right? It's going to go at v constant. Let's do a free body diagram to figure this out. Yes, excellent idea. Thank you. So here it is right here. And mg is pulling it down, right? Normal force is pushing it up. Yes. And now what I'm going to call is the push force. Okay? You're only responsible for 4 forces: gravity, normal, tension, friction. But then when we push something, it's like a normal force. So occasionally we'll give you a new force where we just say there is a force applied. So don't panic if it's not one of your 4. For your hand, I usually just call it F push. Right? F push forward. It is a normal force, basically. It's just like a normal force. It's normal to your finger when your finger presses against it. But just to be more clear, to not mix it up with the other normal forces, we call it F push. And since it's sliding, these two surfaces are sliding, there's a kinetic friction force between them. Right? So there's your free body diagram. It looks very balanced, right? So apply force, and the answer is yes, if, and let's see what has to happen in the y direction. The normal force magnitude just equals mg. That's boring. Sum of the forces in the y. We got normal up minus mg down equals 0. So the magnitude of the normal force is equal to the weight. Boom. There's no angles involved. But let's look to the right. Sum of the forces in the x. Sum of the forces in the x equals, in this case, also 0. Right? Because constant velocity. Right? We're moving at a constant velocity, so A is 0. Well, what are they? Well, it's the push force, which I can tell is moving to the right. If you want, you can multiply it times cosine of 0. And then there's the friction force, which I can tell is moving to the left, so I'll put a negative. If you want, you could say times the cosine of 180 to get the negative. It's that same thing we were doing. A equals 0. So the answer is you just have to push with the kinetic friction force, which you know. Right? You'd have to push at mu kinetic friction times mg. Fk, we said by definition, is the kinetic friction coefficient times n, and n is mg. Right? So there's the whole thing. All right. So when I do that, when I push it at constant velocity, it's like I'm some sort of experimental genius that I can push it exactly. I'm calculating in my head mu k. Mu k is about 0.6, 0.6, okay, 0.6, and the weight is about... No, I'm just here intuitively. It's easy to push at constant velocity, especially if you were in marching band, right? Yes. All right. So another thing about that experiment that throws people off, we'll do more complicated problems in the second half, but let's just talk about some more basics real quick. Okay, yeah, this is just for fun, and then we'll stop. Yes, and this answers the question somebody asked, which is what's going on with the normal for which one is bigger, right? And the question that you could ask is, this isn't just Aristotle, you might ask this, how do you get to v constant? You get to, so this will be a good review going back to kinematics graphs, right? It's not moving, I apply a constant force, and now it's going at a constant velocity, and I stop and it stops moving. Well, there had to be some acceleration. The force couldn't have been constant the whole time. So it's sort of like the trajectories. I say ignore the part where we throw it. Just think about when it's in the air. The same thing would be true in this problem. You'd be told something is being pushed and is already moving at a constant velocity. But sometimes people really want to know things, okay? Right? So it's good to think about this a little more carefully. And let's look at the history of the velocity here. It's actually kind of interesting. Time, velocity of this whole experiment, it was 0 for a while, and then I got it up to some constant, and we pushed it for a while, and then everything just stopped, because I stopped. So there's your velocity. It looks like that. Let's plot the acceleration under that. All right. What would the acceleration look like? Well, it's just sitting there at 0. Now the velocity increases, so that's like a spike in the acceleration. Oh, like that, like the girl on the trampoline. But then during this time, the acceleration is 0. The slope of this line is 0. dv dt is a, right? So there's no slope, no slope, no slope. And then you get a negative thing like that. For a little bit of time, there's a negative acceleration. So that would be there, right? Interesting. Let's put the force on here. Okay, so this is an axis of the force of push that I pushed with. I'm going to put labels on it that are equal to the values of the coefficient or of the static and kinetic friction. Okay, it's not a plot of static or kinetic friction. We're just going to put values like that on it. Okay? So what this would say is that here, what did I have to exceed? I must have exceeded the static friction force. I must have exceeded mu k or mu s mg cosine theta. There's not even a cosine. I must have exceeded mu s mg, right, times the normal force. So I must have gotten all the way up to f or a little f static, like the maximum value. So I must have pushed really hard like this and gotten up here. And then it starts to slide. And then it goes constant velocity. So the kinetic must be right there also, but it actually is always a little bit less, F kinetic. So I accelerated it, but then I went to a force that was equal to mu s times ng. So I actually come down a little bit, like that. Right? So the answer is the static friction coefficient is always a little bit bigger than the kinetic one, for the exact reason that you were thinking about. If they were equal, it'd be hard to define what happens right when you hit it. Does it move or not move? Well, it's always slightly bigger, so it takes a little bit of a push to get it going, and then to go at constant velocity, you pull back. And you almost feel like you can feel that if you push a block. Kind of to really push a block at constant velocity, you push it, and you can almost sense that you're pulling back to make it go constant velocity. It's really in your head, but it feels that way. What happens here? What force stops it? Kinetic friction stops it. Right? So what happens here is I stop pushing. I go to 0. If I stop pushing, is the total force on the block 0? Nope, it's still moving. Right? So I stop pushing here, but it still feels a kinetic friction force because it's still sliding, but it rapidly stops it. Right? The kinetic friction decelerates it and it stops. So actually why it starts and why it stops are different. Different forces. My push started it and kinetic friction stopped it. Okay? All right, so that's it for friction. I had one problem that was so trivial it would have been boring and you'd have fallen asleep. I'll do it on a video or something so you can fall asleep at your computer. So let's take our break and then we'll do tension.